And at this point, I'm going to go ahead and introduce the gentleman who will be providing the science seminar this morning, really the results of the LUX work. Dr. Rick Gaitskell from Brown University and Dr. Dan McKinsey from Yale. Guys, if you'd like to come up, and we'll go ahead and start the seminar. Just to point out, after the seminar, we will have a 15-minute period for what we're calling technical questions. We have a number of scientists who are on the phone, and give them a chance to ask questions about the technical nature of the work that Dan and Rick will be covering. So, okay.
So do we have the... Can everyone hear me in back? Is the mic working? Thank you.
Dan, I should just mention that one statistic is that we've already crashed this Sanford Lab website. So many people are on that we've had to switch to the public broadcasting website.
So welcome to the first science results from the LUX dark matter experiment. It's a very exciting time for us. I'll be giving the first half of the presentation, and Rick Gaitskell will come in and tell you about the final results, or the initial results from the LUX dark matter experiment. You can learn more about LUX by going to luxdarkmatter.org. And thanks to SURF and the LUX team for these fantastic results. So backing up a bit, why are we doing this? Tell you a bit about the composition of the universe. As you, I'm sure, have heard in the news, the Higgs particle has been discovered. The Higgs is the last puzzle piece for the so-called standard model of particle physics. It makes everything fit together nicely. All these particles, quarks, gluons, leptons, the things that make up ordinary matter are all encompassed in the standard model. But as successful as the standard model is, we know there's more physics, more phenomena, more principles beyond the standard model. The standard model only describes about 5% of the universe. The remaining 95% is in the form of dark energy and dark matter, and the fundamental nature of those is essentially unknown. And the evidence for dark matter and dark energy come from astrophysics as well as cosmology. A bit more about dark matter. What is dark matter? Dark matter is the stuff that holds galaxies together. It's the primary source of gravitation that holds galaxies together, galaxies clusters together. If you look at the velocities of stars going around galaxies, they're whipping around galaxies much faster than they could if you only counted the gravitational stuff in stars and gas, the things you can see. Those galaxies would fly apart if it weren't for the dark matter. You can also see dark matter in the effects of gravitational lensing. Light is bent around large gravitational objects, and then like galaxy clusters and galaxies, and then you can work out how much matter is in between. There's a lot more matter there than you get just from stars and dust and black holes and such. And also in the cosmic microwave background, the fingerprints from the Big Bang, which have mapped out cosmological properties in incredible detail, there's very clear evidence for dark matter as well. The dark matter makes up about 27% of the energy composition of the universe. It has to be stable. They're stable particles. They're electrically neutral. They're so-called non-baryonic, meaning they're not made of neutrons and protons and all the stuff that makes up the periodic table of the elements. It's something else. And they're cold, we say non-relativistic, moving much less than the speed of light. Estimated density is about 1/3 of a proton per cubic centimeter where we are in the Milky Way. And as I said, we know this is not a standard particle, it's something new. Some of the names of the candidates are WIMPs, axions, dark photons. There are a number of ideas that physics theorists have come up with to explain this. So we'll be talking about WIMPs today. WIMPs is what LUX is looking for. We're nerds looking for WIMPs. And it stands for weakly interacting massive particles. Okay? That is, these are particles that only very rarely interact with ordinary matter, much like a neutrino does. We know neutrinos exist. They're emitted in huge numbers by the sun and by radioactive decay. WIMPs would be like that, but heavier. They'd be formed in massive amounts in the Big Bang. They would freeze out in the early universe and decouple from ordinary matter. Okay, and then really only interact with it gravitationally after that. And they would exist today at densities of about 1,000 per cubic meter. And physics theorists come up with new ideas for new physics beyond the standard model. Some of those are called supersymmetry or extra dimensions. There are many theories, and many of them predict natural candidates for what could be the dark matter. Supersymmetry predicts a neutralino. Extra dimensions predict something like called a stable Kaluza-Klein particle. There are many examples of this in physics. So what are we doing in LUX? We're looking for those dark matter particles actually scattering, interacting with ordinary matter. We know they have to interact with ordinary matter from how they had to have been produced in the early universe. And you can think about what is the rate. The rate of those events in your detector is something like the number of atoms in your detector times the density of the dark matter times some cross-section, or it's like a probability that the dark matter can scatter with ordinary matter, times a characteristic velocity of the dark matter. Now we're moving around the galaxy at hundreds of kilometers per second. The dark matter is whizzing around the galaxy at hundreds of kilometers per second. A typical velocity scale is 220 kilometers per second, and then when a dark matter particle scatters, it gives some 10 keV. This is an X-ray-like energy. It's a very low energy for detecting individual particles. And so we have quite a challenge. We're trying to see these very low energy events. We need a detector with extremely low intrinsic backgrounds, a very low energy threshold. Gamma rays are all around us. We need to be able to reject those backgrounds. We need to have a scalable instrument to boost this N number to get more sensitivity to sigma, this cross-section. And to avoid backgrounds from cosmic rays, we have to go deep underground. That's where SURF comes in. Okay, so this is a complicated slide, but it gives you a basic picture for what the figure of merit is for this field. We look at dark matter nucleon, that is proton or neutron cross-section. Basically, this tells you how probable it is that it's going to interact, versus the dark matter mass. We don't know what the dark matter mass is. It could be anywhere in this range. Okay? Previous experiments have excluded cross-sections above this line here. So in the green shaded region, that's regions that have been excluded experimentally. And eventually, we will reach a limitation in that neutrinos will create a background. It'll be difficult to go below this dashed line. But there are many theories that live in between its current limits and this neutrino background. And so current technologies are pushing through this parameter space, testing theories like shown in the pink and the red here, or in the green, testing these theories to see if those explain what the dark matter is. Okay, so how does LUX work? LUX is a so-called two-phase xenon detector. Its liquid xenon provides the mass. Gaseous xenon provides an amplification medium for individual electrons. If you have a particle that comes in, scatters in the liquid xenon here, it'll produce a flash of light. That flash of light is detected by photomultiplier tubes, or very sensitive light detectors, detect individual light particles or photons. We apply an electric field to the detector, and that causes electrons from the event to be drifted up through the liquid. And we extract those electrons into the gas. And in the gas, those electrons bang into other xenon atoms and make those xenon atoms fluoresce. So we get 2 pulses of light for every event, at least. From a dark matter particle, it will scatter once, produce an initial flash of light, charge comes up, gives you a second flash of light. We call those S1, the first signal, and S2, the second signal. The time between those signals tells you how long those electrons are drifting. It tells you the depth of the event in the detector, what's the Z coordinate of the event. And the light pattern in the photomultiplier tubes, say here, tells you where in XY, the other 2 dimensions, where the event occurred. So this is very, very powerful. We have few millimeter position reconstruction. We can use this to eliminate events from the edges of the detector. We can reject anything that multiple scatters, gamma rays, neutrons, backgrounds like that, will almost always multiple scatter. Give you multiple signals coming in a very short time period. We can easily reject those events to be able to be more sensitive to the dark matter particles. Also, gamma rays, which are our main background, give you a higher ratio of this S2 compared to the S1. So this ratio tells us another way to reject background, which is quite effective. This ratio of the second pulse of light to the first pulse of light gives us gamma ray rejection and other beta-like events. Here's a schematic. So here's LUX. It's a mile underground and below us here. And it's in a titanium tank here, or a phone booth-sized titanium tank. in the middle of a 74,000 gallon tank of water, ultra clean water. The water shields the detector from gamma rays and neutrons that are produced by radioactivity in the rock. Okay. The detector itself is made of very low radioactivity materials, very low contamination of uranium and thorium and potassium, things that can create gamma rays. And so here's the bottom array, here's the top array of phototubes, about the size of the instrument. You know, it's pretty small, 50 centimeters-ish, bright cylinder. We have 370 kilograms total of xenon in that titanium vessel. There are 250 kilograms of active liquid xenon within our time projection chamber, within our active readout. And the region inside of that we look for dark matter, it's so-called fiducial mass, is about 118 kilograms of liquid xenon. So I should say that we benefit from an extraordinary lab support. We are down in the Davis campus that Mike just told you about. Here's a schematic of where we are. It's a 2-level laboratory. Here's a photograph of the inside. It's a high-tech, clean laboratory with all the services you need to do a top-flight experiment. So we're very grateful for all the support we've gotten from the lab and all its staff. And from the LUX collaboration, it's about 100 research from 17 institutions. You know, people are coming here to do excellent science from the United States, all over the country, from the United Kingdom, from Portugal. Here's a recent photograph from a collaboration meeting, and here you see the various institutions. We lost one of our founding members recently, Dr. James White. James White was a key innovator in liquid xenon, this two-phase xenon detector technology, a real leader and innovator in the field, one of the creators of LUX, and he's very much missed within the collaboration and outside. Here's some photos of the instrument. Here's LUX within that water tank. Here's the titanium tank. It's lined with white reflective material. There are photomultipliers here to look in the water. Here's some of the copper arrays that hold the photomultiplier tubes. Here's one of these photomultipliers, specially made for detecting liquid xenon scintillation light and very low in radioactivity. And here you can see some of the Teflon reflectors that we use to efficiently collect light from throughout the inside of the instrument. We really care about detecting every photon that we can because that sets our energy threshold and our dark matter sensitivity. Some more photos of the construction. Some of the graduate students putting this together. It's a terrific technical training for students. They can put on their CV that they look for dark matter in an underground gold mine, and we did one of the most compelling experiments in the world. Go on and stay in physics or go to industry, make use of their excellent technical skills that they've generated working on LUX. Here's some more photos of supporting systems. We have to purify the liquid xenon continuously. We require sub-part per billion levels of contamination. To do that, we circulate the xenon. Here's some photos of the system. We have to apply high voltages into the cryogenic system through we use a novel high voltage feed through. We use liquid nitrogen cooling with a thermosiphon system that hasn't been used in other such dark matter experiments that's novel to LUX. Here's our xenon storage and recovery system. We can recover the xenon out of the detector if we need to. And that was very important as well. A lot of gas handling, electronics. Okay, so timeline. LUX was funded in 2008 by the Department of Energy and the National Science Foundation. We started designing and building the instrument. We did some first runs of LUX in an above-ground laboratory, completed its SURF in 2011. We moved in, did commissioning runs. Underground laboratory was completed at SURF in 2012, and we moved underground July of that year to its new home in the Davis Cavern within that water tank. We started cooling down in February 2013. We condensed xenon with only just 3 days. We condensed all that liquid xenon from gas phase to liquid phase in February 2013. Started purifying that xenon, calibrating the instrument. That commissioning was completed in April 2013, and then we started an initial 3-month WIMP search. And the first results you will hear about very soon from Rick. After this, we're going to do a full year-long WIMP search in 2014 with a result in 2015, so we will keep running. Okay, so we have exceptional technical performance. We've really been firing on all cylinders. We have very low background at low energies. This is unprecedented within the field at low energies. We have a very low ratio of krypton to xenon. This was a technical challenge. Krypton is slightly radioactive, so we had to remove that to parts per trillion for the experiment. We have an electron drift length that is over 130 centimeters. That is, an electron produced in the detector can move over, on average, longer than 130 centimeters before it's absorbed by an impurity. And compare that to our 48 centimeter drift length within the detector. We're doing quite well there. One thing where we really do well is the light detection efficiency. This combines our light collection and the efficiency of the photomultiplier tubes. This is extremely high at 14%. And we have a very good electron recoil discrimination based on that ratio of charge to light, S1 to S2, given our drift field. On the right, you can see how the electron lifetime improved that over time. It came up very quickly from the beginning of the run. And so our purification systems performed admirably. And here's I just had to show this, a big photo of the detector installed within the water tank. There it is, mile underground. So a typical event, these are real waveforms from a 1.5 keV gamma ray scattering event. This is typical. Really incredible detail and precision you get on these photons and on the charge-induced fluorescent signal. And then the time between here gives you the depth of the event. And you can see the signal across the various photomultiplier channels here. And give you an idea for the time scale, some microseconds, tens of microseconds between S1 and S2. I mentioned we get position reconstruction. We get Z, the depth, by the time between S1 and S2. Electron drift speed measured to be 1.5 millimeters per microsecond. To get the XY position, we use so-called light response functions, is iteratively determining the response of the photomultipliers to the S2 light depending on the position of the event. And then we can invert that and determine the positions of the events. And you can see we have terrific resolution. We can even resolve some of the gate wires in the detector. These are wires here, 5 millimeters between them, and you can see we can even resolve that within the instrument. We have incredible position reconstruction. Another thing we really focused on LUX is the calibrations. And we, more than previous experiments, focused on using calibrations that we could dope into the experiment. That is, put a gas into the instrument, let it move around inside the liquid xenon, give us events that we could use to calibrate the instrument, and then we would remove or let that radioactivity decay. So one of the tricks we use is called Krypton 83M. It's a krypton gas with a 2-hour half-life. Here's one of the sources that we put in the instrument. In the gas system, we could basically put that into our xenon gas stream. It flows into the detector, disperses through the instrument, and then allows us to calibrate in great detail. So here's some images. Give you an idea for the resolution we get in determining the response of the instrument using over 1 million Krypton 83M events. Okay. So we've mapped that out in great detail. Another thing we did that was new was we used tritiated methane. So we can put that into the instrument and give us a wide band calibration of how well we can reject beta-like events from gamma rays or beta decays. This gives you an endpoint energy of 18 keV and allows us to determine the electron recoil S2 to S1 ratio with unprecedented accuracy. And then we can remove that methane fully by circulating the xenon through the purification system, and that's extremely effective. And then we can go back to low background conditions. So the krypton would just decay away and we'd be back to low background conditions. The tritium we could just remove and we'd be back to low background conditions. And this is extremely effective. So more calibrations. So here you get the so-called charge to light ratio band. This is the logarithm of the charge to light ratio. This is the band you get from electron recoils from the tritiated methane. So the blue line is the central value. The red line here is the central value you get from neutrons or nuclear recoils. That's where we expect our WIMP signal to live, our dark matter signal. We can independently calibrate that with neutrons. We use an americium beryllium and a californium-252 source. These are very low activity sources used to calibrate the instrument. It's a very sensitive instrument. We don't want too much activity. And here you can see the predictions that we get from a model from the available literature on the response to nuclear recoils, as well as the simulation of the instrument. And you can see that that agrees very well with what we see in the instrument. So quantifying the electron recoil discrimination some more. If you think about over our dark matter search range, what's the probability that an electron recoil event will look like an average a nuclear recoil event? That is, with 50% nuclear recoil acceptance, what's the probability that you can reject that event? And we measure about 99.6% rejection, which is excellent. And you can look at that as actually counting events in the tritiated methane data set, or you can look at fitting that data set and looking at what you would predict from the outliers of that Gaussian distribution. And that's shown here. Okay, the key thing is we need to know very well what is the light yield and what is the charge yield for the WIMP events. Okay, and what we use is something called the Noble Element Simulation Technique. It's a database based on the canon of existing experimental data, okay, on nuclear recoils and liquid xenon. Here you can see in the data points here and in these dashed lines, results from previous experiments, both underground and dedicated experiments in the lab, measuring the light production relative to gamma rays. Okay. What we use in LUX is this line here. Okay, this step here, and then following this blue curve up. Okay, this is a very conservative assumption on our light yield. Okay, and further, we assume that, as predicted in simulation, there should be a little bit of electric field quenching of the light signal compared to at zero field. So we incorporate that into our models. It's about a 20% effect in the reduction of the signal that we would get. So to be conservative, we include that in our predictions for our WIMP result. Also, you would expect that the signal continues to decrease, but it stays finite down to very low energies. We actually, to be conservative, assume that signals, the light and charge signals, both disappear below 3 keV nuclear recoil. Okay, and that's again to be very conservative so that we're not making any assumptions about this behavior below where there is experimental data. Okay. So with that, I'll turn over to Rick. Rick's going to tell you all about the dark matter result.